I will begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for your creation, that we can study it, and just pray that you'd help us to understand it a little bit better today, Lord. In your name I pray, Lord Jesus. Amen. All right, so, yes, let me find that example. So I think the example is really pretty simple. It is just if I can write it out, I think it's just a wire, with constant resistance or whatever, and you can imagine current flowing, and as that happens, you've got a magnetic field and you've got an electric field, right? And so you can calculate then the Poynting vector, and then, well, let's just do it. All right, so here we have current. Come on. Example 1. So I'll draw it vertically because I like that better. So here's the z direction, and we've got current flowing this way. All right, and this distance is L. All right, so first of all, the electric field, the magnitude of it should be V divided by L, because we're talking about a uniform situation here. So E times L would be equal to V, and of course V is just the difference in voltage from the top to the bottom of this thing. So let's see here. All right, and so I think the electric field would be pointing, like this. All right, and of course the current flowing. So we also have a magnetic field, right? And we want to calculate the magnetic field at the surface. So this distance here, I think it's radius A. So the magnitude of the magnetic field is mu naught I over 2 pi A, right? So I guess in terms of direction, we've got a z hat on the electric field. In terms of the magnetic field, we've got one of these handy-dandy phi hats to describe how it's circling around, right? The magnetic field lines are encircling the current like that. And we're assuming it's like a long, we don't want to fuss with any kind of weird end stuff, so we're assuming that it's long enough that we can use the simple formulas. Then we can calculate the cross product of the electric and magnetic fields, right? So E cross B, you got yourself mu naught IV divided by 2 pi AL. And if we look at z hat cross phi hat, the way that works, of course, is you got your s hat, your phi hat, and your z hat in that order. That's the cylindrical coordinate system. And so if we're up against z hat cross phi hat, that's a minus s hat. So minus s hat like that. Okay, so this is the Poynting vector is what? 1 over mu naught, right? E cross B. Whoa, can I just stop and appreciate this marker? Good night. That is a, if all markers were like this, I might believe in whiteboards. I don't know, wow, that's nice. Anyway, so minus IV divided by 2 pi AL, of course, S hat. All right, so last class we worked out a relation. What is the Poynting vector all about? What's its what's its deal? What's its function, right? Energy flow, right? So, yeah, right. So here we can calculate dW dt, the energy flow, is equal to minus the integral of s dot dA. Now, there's another term that was based on the time derivative of the energy density, right? The integrated, I'm trying to remember what it, I mean. The term I'm leaving off here, if I can find my way back to it. Give me a second here. I'll write it second, since it's nothing, ddt of the integral over the volume of 1/2 of epsilon naught E squared, 1 over mu naught B squared d tau, right? That's the total thing we derived. But in this particular example, it's not time variant. So the energy, and the volume I'm talking about is literally the, and of course this was the boundary of the volume, right? So what volume am I talking about? I'm talking about the cylinder, all right? I'm talking about the cylinder. And so as we think about the work being done, well, this is 0 because there is no time dependence. So we don't even need that. We just need to integrate minus s dot dA. And so that is, let's see here, IV divided by 2 pi AL. Those are all constants. And then we've got the integral over the boundary of V of, well, s hat dot, well, what's dA? Well, we can just do s hat dA, and this is just for the, well, fine. Let me write it out this way. So of course, technically speaking, the boundary has, the top and the base, right? But these have what? Like dA, z hat dA, right? And down here you got dA is minus z hat dA. So obviously those don't contribute anything. And we need only consider the side to the cylinder, which is s hat dA, right? And so that just gives us IV over 2 pi AL times, well, the area of the side, which is what? What's the area of the side of the cylinder?
2 pi AL.
2 pi AL, right. And lo and behold, the work done by a resistor with current I flowing through it, with voltage V dropped across it, is So now you can tell your friends that you can now calculate the power developed in a resistor. And they too can do that if they can only learn the Poynting vector and how to do this integral. Right? Obviously this is not the only way to understand this result. Right? We're just kind of showcasing that oh, come on. The point is probably in Xfinity. No talk, no answer. All right. So there we go. So yes, of course, the power. And so does that make sense? The reason that the Poynting vector is pointing into the, that's resistively, that's the flow of energy. It's flowing into the resistor, right? It's heating it up. That's what's happening. So, all right. So that was just an example of Poynting's theorem. That brings us on to the next order of business, which is Maxwell's stress energy tensor. All right. So what we're up against here is we're trying to understand the force on charges in a volume, let's say V, given by, well, what's that given by? It is given by F equal to the integral over V of the electric field plus the velocity across the magnetic field times the charge density d tau, right? So can we repackage that a bit? See if we can repackage this here just ever so slightly. All right. So we can say that that's the integral over the volume of rho E. Well, nothing much to say there, right? Just factor the rho out. And then plus, what is rho times the velocity? What's that? So that's the current density. Rho times the velocity is the current density. So this gives us J cross B d tau. So in short, we have that this quantity right here, he calls it little f, which is equal to df d tau. It's the force per unit volume right, due to the electric and magnetic fields acting on the charge. So now what we're going to do is we're going to rewrite little f using Maxwell's equations. All right, Maxwell's equations tell us that the divergence of the electric field is rho over epsilon naught, right? And the curl of the magnetic field is mu naught J plus mu naught epsilon naught partial E partial T, right? This is Maxwell's, Ampere's law with Maxwell's correction. So if you take these two gadgets here, we can trade our F for, in fact, my rho I trade for a epsilon naught times the divergence of E. And then, all right, great. Plus, let's see here, what's my, oh, and that's times what? My bad. Don't forget, there's also a what? An E. So it's the divergence of E times E, which is kind of funky. And then my J, what's my J? My J is 1 over, oh man. Oh, sorry guys. Yeah. Sorry, I'm remembering later in the derivation, and I'm like, this isn't what I remember. That's because I'm like 5 steps ahead in my memory. So 1 over mu naught curl of B minus epsilon naught partial E partial T, right? The mu naughts, they be canceling. All right. notice that, let's notice a couple things. One of the things we should notice is that the time derivative of the cross product of E and B satisfies product rule. So you got partial E, partial T, cross B, plus E, cross partial B, partial T. Right? Now we've used 2 of Maxwell's equations so far, but why use 2 when we could use 3? Right? We also know Faraday's law says that the curl of the magnetic field, wait a minute, no, I already used that one. The curl of the electric field, do I need that one yet? Sorry, I've lost my place. Wait, what? Oh, yeah, duh. Minus partial B, partial T. All right. Oakley dokley. And, all right, so let me kind of show you what we're about to do. All right, so it's just algebra, but let me try to guide us through it. We've got a, see this? We've got up here. Now, I'm missing something here, aren't I? Because, oh, come on, guys, don't let me get away with this. What I have written so far is just J. That's what? Crossed with B. I was like, how can I do? Oh, that's because I don't have the correct thing yet. All right, there we go. Feeling better. So now, you see, I've got this handy-dandy partial E, partial T cross B term, right? And I can trade that for what? I can trade partial E, partial T. I'll put a minus on it. Actually, I won't. Cross B, change my mind. That's equal to partial T of the cross product of E and B minus E cross partial B partial T. All right? But notice that this is partial T of E cross B, and I can trade out this minus partial B partial T for a plus E cross the curl of E. Using Faraday's law. Putting that all together, we have F is equal to epsilon naught, divergence of E times E plus, well, I'm going to leave the del cross B term. I'm going to leave like this and that out for last. Right now we just have minus epsilon naught partial T. Sorry, I'll try not to do too much in one step here. All right, and then I still had the plus 1 over mu naught curl of B cross B here. All right. Well, you see the pointing vector coming up here, right? See that? Because we can get that out of the way. And, all right, so apparently we've got epsilon naught times the divergence of the electric field times the electric field minus E cross the curl of E, close parentheses, plus 1 over mu naught and let's throw in, hey, let's use all of our Maxwell's equations. So the divergence of B times B, oh, notice that, see the way these are? I've got the curl second and the curl first, so if I flippy flop it, I get a minus B cross the curl of B here. And then, of course, I've got, minus golly, epsilon naught mu naught partial S partial T, since S is 1 over mu naught times E cross B, right?
Divergence of B.
Ah, yes. Where did the divergence of B come from? Good question. Anyone care to answer this question?
Oh, you're adding 0.
Mm-hmm. It's the no monopoles equation. Of course, I can add 0, right? So, yes. Say, who said adding 0 never did anything for you? All right. And you know how I say that, like, I sometimes doubt the need for the front cover identities? Well, I think this is that place where the identity that I'm like, that's a weird identity. It doesn't seem like we need to use that one. Well, here's another place. So product identity number 4 on the front cover says that the gradient of the dot product of two vectors, this is not the magnetic field at the moment. This is just two vector fields A and B, all right? That is, as it turns out, A cross the curl of B plus B cross the curl of A plus A dot nabla acting on B plus B dot nabla acting on A, of course. All right. And so from this, if we look at nabla E squared, that's nabla E dot E, right? E squared is E dot E. Yeah? So that would give us what? Yeah, we got, oh, you see there's 2 of them? Oh, cool. So 2, thank you, saving me writing. I like it. E cross the curl of E, right? And there's 2 of these as well. 2 E dot nabla E, right? And look, we have, what do we have? So what we then have is the following identity. E cross the curl of E is equal to, apparently, 1/2 nabla E squared minus E dot nabla times E. The 2's be canceling. Likewise, same thing for the magnetic field. B cross the curl of B is 1/2 nabla B squared minus B dot nabla times B, right? So we can replace this guy And we can replace this guy with this guy. And, right, appropriately. Oh. Sorry, I'm trying to get through this fast enough that we still have time for an example, but the algebra here, kind of formidable. If I was smarter, I'd just write down the answer. But anyway, here we have epsilon naught. We've got, as it happens, notice the minus. So I need to account for the minus. So I get nabla dot E times E plus E dot nabla times E, and then apparently minus 1/2 nabla E squared. And then over here we got 1 over mu naught nabla B, divergence of B times B plus B dot nabla times B minus 1/2 nabla B squared, and then close parentheses minus epsilon naught mu naught partial S partial T. Great, googly moogly. There it be. I think that's, let me see where I am. Yeah. All right. And so then, fine. We have that. Actually, can I erase the, I can erase this part up here, right? We don't need that anymore, right? Okay. See, if I was teaching this course more often, I would relegate large chunks of what we're doing into homework. And just be like, by your homework problem, such and so forth, this happens, you know, and then that would make you guys take ownership of it. But as at the moment, the only thing I have to do is put it on the test. So. Anyway. All right. Oh, I think my page numbering, well, what? I used it. I used it to drive these two things that I've just erased, and get that. That allowed us to replace the blue part and the purple part with the corresponding nabla del E squared and nablas and those terms. All right. So definition. Tij is equal to epsilon naught EI EJ minus 1/2 Kronecker delta IJ. Oh, come on. Kronecker delta IJ E squared. All right. Plus 1 over mu naught, same pattern but with B's. So BI, BJ minus 1/2 Kronecker delta IJ B squared. All right. This is Maxwell's stress energy tensor. So let's see here. I could build it as a genuine tensor. I mean, you could write this. T is equal to like the sum. So I equals I and j 1 to 3 of like Tij dxi tensor dxj, whatever that means. Well, let me tell you what it means. where this is notation I'm introducing right now. If we take t and we evaluate it on a vector v and a vector w, that ends up being like the sum ij equals 1 to 3 of tij dxi of v dxj of w. That's the way that works. And so in terms of a formula here, that's the sum I and j equals 1 to 3 of tij, and that is the ith component of v and the jth component of w, but fine, I don't know. Later in chapter 12, we'll have some other conventions to work with, but at the moment, I'll just leave it like that. I don't know, have we put indices up on vectors in here? I guess we haven't. I'll just leave it. Anyway, the point is, in terms of a formula, you could write it this way. It's v1, v2, oopsies. My indices are showing v2, v3, and there's a matrix. So the question is, like, what is a tensor, right? This much I can tell you, a tensor is bigger than a vector field. It's got, in this case, it's a symmetric tensor. So truth be told, it's got 6 independent components because it's pretty easy to prove here, right? Like theorem, lemma, whatever you want to call it, observation. Tij is equal to tji, right? See, look at the formula that defines it. I and j appear symmetrically. So like it's symmetric. So like that matrix that I just wrote down is in fact a symmetric matrix. So we can write this kind of symmetric, this kind of symmetric matrix in terms of just like a row matrix column product, if you like. So look, this is a way we could think about T in terms of a contraction over a pair of vectors like this. Griffith has these wild double arrow symbols and stuff with his own particular quirky way of defining things. Fine, whatever. I don't care. I'm not going to engage in that. I refuse. I suffered through it as an undergraduate. I refuse to now. But anyway, what I want to define for you guys, if I can find my calculation, is, all right, so listen, this up here is unambiguous. The Tij formula at the top, whatever else, like you don't have to understand what I just wrote below that and above the line. This is more for Sam and for people who've had my advanced calculus, all right? That might make some sense from that perspective. But anyway, if I look at the sum I equals 1 to 3 of partial I Tij, all right, then that is the sum I equals 1 to 3 of partial I of what? Of epsilon naught times EI EJ minus 1/2 Kronecker delta IJ E squared, close parentheses, plus 1 over mu naught BI BJ minus 1/2 Kronecker delta IJ B squared. All right. And if I work through that, after a little bit, that is equal to epsilon naught times the divergence of E times EJ plus E dot nabla EJ minus 1/2 the jth derivative of e squared, close big old parentheses here, plus 1 over mu naught nabla b dot, the divergence of b times bj plus b dot nabla bj. What did I just do? Oh yeah, it's fine. bj. Minus 1/2 partial j of b squared. And all right, so I did that calculation. I was like, oh, wait a minute. Okay. So if I take the derivative of the stress energy tensor, where I'm summing I against the derivative with respect to the ith coordinate, I will recover the same terms that are in what we just derived over here. But it's not quite the right pattern because you see over here, I have vectors, right? Whereas on the other one, I just have what? Like the jth component. See that? See the difference? Vectors versus components. So to fix that, I took this and I just said, oh, okay, well, what if I just do the sum over I and j equals 1 to 3 of partial I Tij times x hat sub j. Then that will be equal to, by essentially the same calculation, that turns, that adds a sum over j of ej. If sum over j of ej is just e vector. So that turns this into an e vector. That turns this into an e vector. Come on. Minus 1/2. And now he would say nabla e squared, because when I sum x hat, when I put an x hat j in front of this and I take the sum, that's the gradient vector acting on e squared. And over here, so you see what we're getting, right? We've found our way back to where we were. And so, in view of this notation, we have that, in summary, f vector, well, I'll write over here. We have found that f vector is equal to the sum I equals 1 to 3, the sum j equals 1 to 3 of partial I Tij parentheses x hat j minus epsilon naught. Oh, I think I need a mu naught there. I've got a typo in my notes. We had, do you guys agree with the epsilon naught mu naught here?
Yes.
All right, so epsilon naught mu naught partial s partial t. So with the stress energy tensor, we can account for all of those terms in the force per unit volume. Now Griffiths calls this contraption right here, his notation for this is nabla dot t double vectors. That's what he calls this. And that's based on understanding his formulas hold if you replace a vector with a vector of operators and make an analogy. And I just prefer to have an explicit formula. This is what it is. And I just worked it out over here. All right, so let's go back to the whole purpose of this, which was to calculate the force on the charges in a volume, right? Oi, oi, oi. I'll do it over here, I suppose. All right. So the force on the charges in the volume was equal to the integral over the volume of f d tau. But after some work, we figured out that that's the integral over the volume of parentheses, the sum I and j equals 1 to 3 of partial I acting on Tij parentheses x hat sub j minus epsilon naught mu naught partial s vector partial t integrated over the volume. All right, so what are we up against here? All right, so what we're up against then is the integral over the volume of the sum. I'm going to rewrite this a little bit differently. Sum I equals 1 to 3 of the ith derivative, right, of the sum j equals 1 to 3 of Tij x hat j. All right, d tau minus epsilon naught mu naught integral over the volume of partial s partial tau d tau. All right, great. Now, this is a what? I mean, if I call this thing, you know, for just for the sake of a discussion here, G. I mean, this is altogether G. This we could replace as like the integral over V of the sum I equals 1 to 3 of partial I GI, right? It's getting boring to write this. This is always the same thing. There's nothing happening over here. Here I've introduced my G vector as the sum j equals 1 to 3 of Tij x hat j. My bad. This is just the ith component of G, right? I mean, my point to you is that's a divergence. Right? That's the divergence. And so what we have then is the integral over the boundary of the volume of the sum j equals 1 to 3 of Tij x hat j, right? Dot, well, dA. of course, minus the other thing. We're not, this is a weird calculation in the sense because it's not, there's not just, what's that? Oh no, I changed it for the, I'm using the divergence theorem.
Or in the line above that.
Oh, yes, thank you. So like, more explicitly, this is the integral over the boundary of the volume of the sum I comma j equals 1 to 3 of Tij x hat j, all right, times x hat I dot dA. Minus epsilon naught mu naught ddt of the integral of s d tau. Now this thing, Griffiths has a different notation for. He calls this the integral over the boundary of the volume of t double arrow dot dA, like that in Griffiths' notation. I think probably like a better notation would be maybe this. F equals the integral over the boundary of the volume. If we take the stress energy tensor, we evaluate it at dA, and we leave the other blank open, and then minus mu naught epsilon naught ddt, the integral over the volume of s d tau. I kind of like that as a shorthand for the more complicated expression on the board there. All right, so I'm afraid to ask if there's any questions. I mean, listen, I'm going to actually flesh out this formula in a specific example next time. I don't want to do it today, obviously, because you don't want to be here until 6. But, and I dream of a world where I can write that example out, scan it in, and then project it. But that's a world in which the scanner's working, and that world is not including today, because somehow the printer is somehow caught up in the Amazon cloud death. I don't even know how, but the secretary has rebooted it twice and it's still not working, so whatever. So the tricky thing here is it's basically got two indices, right? So if you contract one of them, you're still left with an index, which means like if you contract the second rank tensor in the physics language with a vector, you're left with essentially a vector. And that's what's going on here, because the force is a vector, so this leaves us with sort of a vector that we're integrating, but it's taking into account how the stress energy tensor interacts with the surface that bounds the volume we're trying to find the force of the charge in. Now, the really cool thing about all this is that we know what F is equal to, right? Like F is equal to the change in momentum, right, with respect to time. So what does this all mean? Like, in the context that, I mean, there's different cases you can think about, but I think there's, one of the cases is if the stress energy tensor was 0, which would happen when? Actually, I'm not sure when that would happen. When would that happen? Just a second here. Let me pause for a second. What's that? Well, that's a good question. What does it represent, right? So we started this discussion with how the third law broke down, right? We have now found our way, after some effort, to a formula that calculates the total force in terms of an integral of this tensor over the area and a time derivative of the integral of the Poynting vector over the whole volume, right? And so what Griffith says on page 370, he's like, if you have a static case, yeah, that's what I'm trying to remember. The static case, if there's no time variation, right? In the static case, we just get what, like integral over the boundary of the volume. And if you'll, allow me this sort of easy notation for it, that's in the case it's static, right? So in the static case, there's no time dependence in the Poynting vector, right? So the net force is just equal to that. And so what he says that Tij is the force per unit area in the ith direction acting on an element of surface oriented in the jth direction. So the diagonal elements, Txx, Tyy, Tzz, represent pressure. The off-diagonal represent shears. The example he then does is to calculate the net force on the upper half of a uniformly charged sphere by calculating basically this. He calculates this over the top half of a uniformly charged sphere. That calculation's earlier in Griffith's done by different means. So we actually will work that out with the stress energy tensor next time. It's a little bit of work, but what's really cool about this is, let me just kind of give you the big picture. We're going to go on and we're going to see that this same stress energy tensor can be used to describe like conservation of momentum in the electromagnetic fields, but also conservation of angular momentum. And the interesting thing is the Poynting vector is going to appear in both. So the Poynting vector on the one hand was having to do with energy density, I think we saw last time, right? What was it? I mean, our flow of energy? Yeah, like what was our continuity equation was what? Like, good grief, I've already forgotten. Don't tell the other physics professors, right? Yeah, say that again? I think that's right. Yeah. So in empty space, right, we had partial u, partial t is equal to minus the divergence of the Poynting vector, right? But we also had the w dt, right, the power was minus d dt of the integral of u d tau minus the integral over the boundary, right, of s dot dA. So the interesting thing, I think, that I'll talk more about next time as well, is that the Poynting vector comes up in the study of power, right, like energy per time developed by the electromagnetic force. But it's also going to come up in the discussion of like force. I mean, you can kind of see it here. I don't know. I had a thought earlier, and now it's gone. I'll stop trying to say the thought I've lost. Maybe I'll find it next class, but anyway. Sorry if this is a bit of a mess, but it's a bit of a mess.